Okay, section 5.6, we're continuing discussing this section, and we're going to talk about trajectories of a dynamical system. Okay, so let me let you copy this example down. Okay, so one thing that's interesting to notice here is that this matrix A is a diagonal matrix. Okay, it's a diagonal matrix. Now, of course, a dynamical system, you don't have to have a diagonal matrix, but I'm just commenting that for this little example, A is a diagonal matrix. And this example is actually example 2 from section 5.6. So, okay, as K changes, okay, you start off with an initial vector x sub 0, and then x sub 1 would equal a times x. The vector x sub 1 would equal a times the vector x sub 0 by the dynamical system formula here. Okay, and then the vector x sub 2, okay, would have to equal a times the vector x sub 1. And you get a sequence of vectors here. And what we're interested in is, or sequence of points, right? We're interested in what's the behavior of the points. In other words, what is the, you know, the sequence of vectors creates a trajectory in two-dimensional space. And we want to know what that trajectory looks like. So, well, what's the first thing that we have to do, class, for this matrix A? What do we have to find? What do we always have to find in chapter 5 for these problems? To ascertain behavior. That's right, Hung. Eigenvalues and eigenvectors. Now, is it going to be hard to find the eigenvalues of this particular matrix A here? No. That's right, Haley. That's right, Hung. It's a diagonal matrix. So what are the eigenvalues? That's right, Hung. 0.84 and 0.64. That's right, Haley. Right along the diagonal. And you learned that. You learned that. And so all we need to do is find the eigenvectors. And of course, we could use, so let me go to the solution here. We could use MATLAB to find the eigenvectors. Okay, they would be easy to find though. Here are the two eigenvalues, here are the two eigenvectors. And we know from what we've learned in section 5.6 that the kth vector, okay, in this trajectory can be found using this formula here. So the kth vector is simply equal to a linear combination, okay, of, well, C1 times lambda 1 to the kth power times the eigenvector V1 plus C2 times lambda 2 to the kth power times the eigenvector V2. And therefore, your x sub k vector will equal C1 times 0.80 to the kth power times the vector 1, 0, plus C2 times 0.64 to the kth power times the vector 0, 1. All right, let me give you a moment to catch up here. We're right here. Let me know if you have any questions. Okay, so, all right, here we are. Here we are. We have now, we know how to find the kth vector xk of this dynamical system. And I have a note here, right here, that as k goes to infinity, this part of the xk vector, the second part here, the second part, goes to the zero vector more quickly than the other part. Why would that be? That's right. Good, Hung. There's a smaller decimal. So both pieces of this x sub k vector involve, like you have 0.80 to the kth power and 0.64 to the kth power. Those are like dampening factors. Those eigenvalues are less than 1. So this eventually, this trajectory described by this dynamical system will have to go to the zero vector, because both of these factors here, as k gets large, both of these factors, 0.80 raised to the kth power and 0.64 raised to the kth power, both those factors go to 0. But the second piece here, the second component, I got to be careful using components. And the second portion of the xk vector is going to go to the zero vector. It's going to disappear more quickly because 0.64 to the kth power approaches 0 more quickly than 0.80 to the kth power. Are there any questions on that? Are we okay with that? All right, who's feeling good? Maybe give me a few thumbs up so far. Hung's good. Want to make sure that Eleanor's good. Abby's good. Wonderful. Thank you. Thank you. So, well, because the trajectory approaches the origin, we call the origin an attractor. It's called an attractor. And if, incidentally, if the trajectory were to move away from the origin, we would call the trajectory a repeller. Okay, so, and then there's even something called a saddle point, which we'll talk about in a moment. But this is an attractor. And in the little picture here, okay, I actually just took figure 1 from the book and made a copy of it. Okay, what they do is they show different trajectories for depending on what? Well, depending on what your initial vector is. Okay, they have these different trajectories drawn, okay, for all these different initial vector x sub zeros. All right, you get all these, I want to be careful, I don't want to mess up my picture, but can you can see that, right? You have all these different trajectories. Okay, so like for this trajectory here on the right, okay, what is this? What is the initial vector here appear to be? What coordinates are for that initial vector? That's right, Benjamin, 3, 3. And okay, well, in that case, 3, 3, the trajectory moves in towards the, I mean, it approaches the origin like that. And incidentally, how are they finding, you know, in order to well, like if you look at the x1 here, for x1, that vector there, x1, they have a you know, they have a specific coordinate here. Okay, they have a specific coordinate. And so they must have for x1, you know, so like for x1, they let k equal 0 here in the formula and found x1. But what about these unknown constants? What about those unknown constants? I mean, what I'm trying to say is x sub 1, okay, would equal this, to find x sub 1, you would use the formula here for x sub k. It's just k would equal 0. But the formula has constants c1 and c2 in it, right? So they must have been found some way in order so that we could plot a, you know, so that we have an actual coordinate with for x sub 1 with like real, you know, real numbers. I mean, they must have solved for c1 and c2 somehow. How do you think they solved for c1 and c2? How do you think they did that? How do you think they did that? Hold on, let me. Good, Haley. You have an initial. Well, look at that. Haley says that the initial state is. Let's see. Let me just read. Haley makes a very good point. If k equals 0, then this term here, 0.8 to the 0th power is 1, and 0.64 to the 0th power equals 1. And so it's clear that C1 and C2 would both have to equal 3. So and that's just a nice example there. Very good, Haley. So basically, to find C1 and C2, you just have an initial condition. How many remember in differential equations to solve for the unknown, an unknown constant? You need an initial value problem. How many remember that from calculus 2 in differential equations? Sure, Justin remembers it, Benjamin remembers it. You need if you have a differential equation and you solve it, you're going to get a general solution. And there's a parameter in there, right? Or there could be multiple parameters. But to solve like for a parameter, you need an initial condition. Well, these are the initial conditions, okay? Like here's an initial condition, and then over here we have a different initial condition, over here. And if it's a different initial condition, here's how the trajectory goes, and they all go to the origin. Are there any questions so far? Okay, so let me ask you. Now, it says here that the direction of greatest attraction is the line through the origin and the eigenvector v2. So the eigenvector v2 is the vector 1, 0. Okay, so let me just the eigenvector, I'm sorry, 0, 1. The eigenvector v2 is the eigenvector 0, 1. So I'm looking at these trajectories, and do they approach the origin do they go in like deep to the origin, or I want to say this the right way. Like if we look like at this trajectory here, look how it goes in to the origin. Look how it goes in there. Look at it. Look at the path that it takes into the origin. Okay, is it going in deep or is it going in shallow? So I want to say this the right way. Let me say it maybe another way. So again, for any trajectory, you have two multiples of two vectors. You have a multiple of vector v1 and a multiple of vector v2. And that determines how the vector moves into the origin. So which we agree that the second portion here, the second portion of the xk vector dies down more quickly, and that's going to leave you with the first portion. Okay, that's going to leave you with the first portion. So even though as the trajectory moves in, okay, towards the origin, what has to be happening to k as the trajectory moves into the origin? What's k doing? The value of k. Is it increasing or decreasing? It's increasing. That's right, Benjamin. So eventually what happens is, as k increases, the second term essentially is not there. And you're left here with the first term. Well, the first term is a multiple of 1, 0. right? I mean, this C1 times 0.80 to the kth power is just some, for any value of k, it's just some constant, and you're multiplying it by the vector 1, 0. Well, 1, 0, is that a vector on the x2 axis or the x1 axis? Is the vector 1, 0 a vector, is that eigenvector on the x1 axis or the x2 axis? The coordinate 1, 0, is it on the x1 axis or the x2 axis? It's such a simple question, everybody's afraid to answer. They might get it wrong. But you know, come on. 1, 0, that coordinate, is it on the x1 axis or the x2 axis? That's right, Nafani. That's right, Hung. It's on the x1 axis. So as k gets large, here, do you see how all the trajectories approach the origin, no matter what the initial condition is? All the trajectories approach the origin, but they all end up, let me see, I want to say this right. They all approach the origin in a way that they are hugging the x1 axis. You see that? How all the trajectories, as k gets large, they hug the x1 axis. You see that? And that's because the second portion of the xk vector just goes to the zero vector more quickly. So the direction of greatest attraction would be a line through the origin, the zero vector, and the eigenvector v2. Initially, when the vectors get pulled into the origin, does it look like initially, when the vectors start getting pulled into the origin, does it look like their approach is that's more vertical or more horizontal initially? You know, look how the vectors are approaching the origin in the beginning. In the beginning, the approach, does it look more like a vertical approach or a horizontal approach into the origin in the beginning? Do the paths look more vertical or more horizontal in the beginning when you start off from the initial condition? The path should look more vertical, right? More vertical. And then as k gets large, they become more horizontal. But because 0.64 to the kth power dies down more quickly, the eigenvector v2 has more of an influence in the beginning on the 0, 1, which is a vertical vector. That has a more influence on the beginning of in the attraction. It has the greatest attraction is in that direction. But then as k gets large, you know, the vectors, the trajectories are more take a more horizontal path into the origin. Okay, are there any questions on that? Okay, let's go ahead here then and go into the ebook. I want to go into the ebook. Okay, and just give me one moment here. Hold on. Try to get some of this stuff off here. Okay, so here you have an example of a repeller. Okay, in figure 2, they show what's called a repeller. All the trajectories move away from the origin. You see that? All the trajectories move away from the origin. Now, in order for that to happen, what would both eigenvalues have to be greater than for an origin to be a repeller? Both eigenvalues would have to be greater than what number? Good, Hung. Good, Nafani. Good, Lewis. All greater than 1. All greater than 1. That's right. That's right. The previous example that we did that you had for your notes was an attractor because both eigenvalues were less than 1. All right, are there any questions on that? Okay, well let's keep going here. Let's keep going. Now, in example 4, you have plot trajectories for this. They call it diagonal matrix D. Look at your eigenvalues here. Here, for your eigenvalues, okay, you have a 2 and a 5. So in this case, you have one eigenvalue that's larger than 1 and one eigenvalue that's less than 1. Okay, what would a trajectory look like in that situation? Well, here's the picture. In figure 3, you have what's called a saddle point. So what happens here is you have in the yk vector, I mean, they call it yk, but we could use xk, right, as well, but they call it the yk vector. You have two terms that are fighting each other because one term is growing with the 2 to the kth power as k gets large. Okay, so I'm looking right here. Okay, so as k gets large, the first term with the 2 to the kth power, that grows. But the second term with the 0.5 to the kth power, that term dies out. So initially on your trajectories, the terms, as k gets large, the terms, as k gets large, the terms will eventually they'll eventually hug the x1 axis because the first term with the 2 to the kth power in it is multiplying the vector 1, 0. Okay, and the second term basically disappears as k gets large. But it doesn't approach, I want to say this the right way, it doesn't approach the origin, you see. It doesn't approach the origin. Okay, it just approaches the x1 axis. The trajectories all approach the x1 axis as k gets large. So they move into the origin, they move in, but then they move out, so to speak. It's like they approach the origin in the beginning, but then they move away from the origin because the first term with the 2 to the kth power dominates when k gets large. Okay, so you've heard of saddle points maybe if you've taken multivariable calculus, you've heard of maybe a saddle point. But this is a saddle point from a linear algebra sense. All right, are there any questions on that so far? Okay, okay. Well, let us keep going here. Okay. So, all right. Another thing that we need to talk about is a change of variable. So, how many remember in calculus? In calculus, for an integration technique, you can make a change of variable. How many recall that? Like a U substitution. Yeah, Abby remembers that. And you know, we can also make a change of variable in a linear algebra sense. So what does that mean? What does that mean? Well, all right, they talk about this here. Okay, and let me just sort of highlight some things here. So the examples you saw with the trajectories involve diagonal matrices. But what if the matrix A were non-diagonal? How would you deal with that? Well, to handle the non-diagonal case, we recognize that the eigenvectors of the matrix A form a basis for n-dimensional space. And we let P equal the set the matrix with the eigenvectors. So of course you know that diagonalization is going to get involved here, right? So all right, you have a sequence where xk equal x sub k plus 1 equals a times x sub k. But what you can do, and maybe I don't want everything highlighted here, what you can do is you can make this change of variable. Okay, you can let y sub k, this new variable, equal p inverse times x sub k. But that means then that x sub k equals p times the vector y sub k. So now instead of looking at x sub k plus 1 equals a times x sub k, instead of looking at that dynamical system, we're going to look at the dynamical system. We're going to look at the dynamical system involving y sub k plus 1. Well, what would that be then? Well, if we take, yeah, I want to, if we were to take p times y sub k plus 1, okay, that would equal a times p times y sub k. Okay, and that's because, hold on here now, one moment. Hold on here. What I'm trying to do is get comfortable with that p times y sub k plus 1 equals a times p times y sub k. Let me see here. You know, I, I looked this over, and now I have, I'm a little bit, let's see. Well, A, like if we keep going with it, A does equal P times D times P inverse. We're assuming A is diagonalizable. And then P times Y sub K plus 1 will equal P times D times Y sub K. But the first step here, where P sub Y K plus 1, or P times Y sub K plus 1 equals A times P times Y sub K, I'm just trying to make sure I'm comfortable with that. I'm going to come back to that, okay? I'm going to come back to that. I'm going to have to think. I mean, it's probably obvious. Let me just see here. Let me write it here. It always helps me to write it. Just give me a moment, class. We'll move on if we have to here. I mean, y sub k plus 1 should equal, yeah, I'm gonna come back to that, class. I'll come back to that. All right, let's just keep moving forward here, because I do want to let's just take it as on faith that it's true now, and then I'll come back to that later. So, all right, so what we have here, hold on, I want to focus on P times Y sub K plus 1 equals, hold on, I don't want too much, I just don't want too much highlighted here. I want to focus my highlights. Okay, so P times Y sub K plus 1 would equal P times D times Y sub K. But then if you multiply both sides by P inverse, you're going to get Y sub K plus 1 equals D times Y sub K. So what happened was you went from a dynamical system where your vectors were x vectors and the matrix A was not diagonal, and through this change of variable where x sub k equals P times Y sub K, we now have Y sub K plus 1 equals D times Y sub K. And that means this dynamical system, if you write it out, the change of variable from Y sub K to X sub K to Y sub K has decoupled the system. It's decoupled the system. In other words, the evolution, for instance, of Y sub 1K is not affected by the other variables, okay, by virtue of the fact that you have this diagonal matrix here. Y1 at time k plus 1 would equal lambda 1 times Y1 at time k. So you've decoupled the system. And you know, this is helpful in terms of basically thinking about what a trajectory would look like if your matrix A were not diagonal. The key here is, hold on here, let me just get rid of, hold on. I highlighted a lot, didn't I? Hold on, class. Let me just unhighlight it. I really highlighted a lot. Okay, so what we can get from this, is that this here, this statement right here. The equation x sub k equals P times Y sub k says that Y sub k is the coordinate vector of x sub k with respect to the eigenvector basis. Okay, so in other words, the trajectory defined by the x sub k vector can be thought of as a linear combination of the eigenvectors of the matrix P, and the linear combination is defined by the vector Y sub k. All right, that's how you have to think about the trajectory. So this amounts to what this amounts to is that when n equals 2, this amounts to using graph paper with axes in the directions of the two eigenvectors. That's what that amounts to. Because the trajectory is a linear can be expressed as a linear combination of the eigenvectors of the matrix P. So if P is a 2 by 2, there are two eigenvectors. So you're essentially using axes that correspond to those eigenvectors. That's how you can draw the trajectory x sub k. So, like for instance, in this example here, okay, show that the origin is a saddle point, and then of this matrix A. This matrix A is non-diagonal, okay, and okay, find directions of greatest attraction, greatest repulsion. All right, well, they find the eigenvectors. Here they are, v1 and v2. The eigenvalues are 2 and, well, the eigenvalues are 2 and 0.5. The eigenvectors are the v1, negative 1, and 1, 1. And then here is the dynamical system. Okay, here's the dynamical system. Now, if you draw, if the axes that you would draw on the trajectory go with the eigenvectors 1, negative 1, and 1, 1. And so if we look at the figure here, figure 4, this is what the if you see, to draw the trajectories, well, by using the basis of eigenvectors v1 and v2, and again, v1 was 1, negative 1, and v2 was 1, 1. You see there in figure 4 how the axes correspond to axes that are going through those two eigenvectors, v1 and v2. Do you see that? See, here's v2, here's v1. So the axes, I mean, you have an x and an x and y axis, right? You do have an x and y axis, but it's not the most convenient. Those are not the most convenient axes for drawing the trajectories, these saddle point trajectories. It's better to use axes v1 and v2, and then you see how the trajectories naturally, you know, they, after k gets large, they approach the eigenvector v2. Okay, I'm sorry, I said that wrong. As k gets large, the trajectories all approach the axis that contains the eigenvector v1. And that's the portion of the xk vector that has 2 to the kth power in it. That's the portion that doesn't disappear with k as k gets large. So you see, by thinking about this change of variable, it helps you to understand how to graph these trajectories using using a more convenient set of principal axes. All right, are there any questions on that? Okay, who feels reasonably comfortable? Reasonably. Well, okay. It's going to take a little time to get comfortable, but I'm, you know, I think we've hit upon the highlights of this section. But are there any questions? All right, I think after you get some practice, you'll feel more comfortable with this. But on that note, let me stop the recording for section 5.6.